Alright, let's look at the 2012 FRQ section. So, it's a typical table Riemann Sum type problem where we're given the temperature of water in a tub at time t is modeled by the strictly increasing twice differentiable function w, where w of t is measured in degrees Fahrenheit and t is measured in minutes. At time equals 0, the temperature of the water is 55 degrees Fahrenheit. The water is heated for 30 minutes at time beginning 0. Select values of w of t are given for the first 20 minutes. Okay, so let's talk about this problem here. It says that using the data in the table, we have to interpret some stuff. We have to estimate w prime of 12. So A, w prime of 12. Well, I think we kind of all know where this is going, right? This is always that first question that I ask you guys. What is the highest level of math you need to solve this problem here? And really, it's just algebra 1. So I'm going to go ahead and just figure out what w of 12 approximately, w prime of 12 approximately is. So I'm going to do that by squeezing it in between this 9 and this 15. So I'm going to go, well, what is w of 15 minus w of 9 over, not w, 15 minus 9? Well, that is 67.9 minus 61.8 over 6. And so it's a good thing this is a calculator problem. I'm going to go and just calculate it. So I got 67.9 minus 61.8. 67, whoa. There we go. 67.9 minus 61.8. And then I'm going to go ahead and divide that by 6. And what do I get? 1.016667. So, I'm going to go and write that down. 1.01667. Using correct units, interpret the meaning of this problem. Okay, well, using the correct units, I'll go and explain that in my answer here as I go to my typing tool here. Well, the rate at which that water is increasing, right? The temperature that's increasing is going to be increasing at this number right here, when time equals 12. So that's all I have to write. So the water temperature is rising. Approximately 1.01667 degrees Fahrenheit when t is equal to 12 minutes. Minutes. Bam. And I think that's good enough for our part A. Alright, let's look at part B. It says, use the data in the table to evaluate the integral from 0 to 20 of w prime of t dt. Using correct units, interpret the meaning of that in the context of this problem. Okay. Well, notice how they're asking us to integrate w prime, but they don't tell us what w prime is. All I know is that w prime is the rate at which this table is changing. So if I had to integrate that rate, which is what they're asking me to do, looks like they're asking me to go from 0 to 20 of w prime of t dt. Well, that comes into play, that first fundamental theorem of calculus. I would get w of 20 minus w of 0, right? And so do I know these two values? I think I do. W of 20 is 71.0 and w of 0 is 55.0. So what is that? 71 minus 55? 16. Okay, well, what does that mean? Well, it means, and we have to use correct units yet again. So go back to my typing tool here. What it means is that the temperature of the water has done what? Well, it has risen by 16 degrees Fahrenheit over the first 20 minutes. Right? If the total change was 20 degrees, that means the temperature of the water had to have climbed or risen by 16 degrees in the first 20 minutes. Okay? So, part C. Now they're asking us to do some more integration work. It says the average temperature of the water in the tub is modeled by this integral here. Use a left Riemann sum with 4 subintervals in the data to approximate the value. Does this approximation over or underestimate the average temperature of the water in those 20 minutes? Explain your reasoning. Okay. So let's go ahead and graph this thing, and we'll see what happens. So part C. I'm going to go ahead and pause for a second. I will come back with this table already done. I don't want to waste your time with you watching me do it. Now that I've got my data all mapped out, let's go ahead and just calculate the Riemann sum. Now, I'm going to go ahead and connect these points kind of in a strange way. I'm going to go ahead and just do a little bit of, something a little bit more odd looking. Now, why am I doing it like this? I think some of you guys might see where this is going. I connected them using different concavities, and I really think that's meant to answer the second part of the question. Now, you don't have to even draw the graph to get points on the FRQ, but I want to try and illustrate something for you guys before we move forward. What I'm going to do is I'm going to go ahead and just draw out my rectangles. Now I'm using a left-handed sum, which means all of my heights are going to get pulled from the left sides of each rectangle. And for those of you who kind of see where this is going, I think you guys kind of hopefully understand why I drew the graph the way I did. That's not to say that the graph definitely grows like this. It's just a means of illustration. Okay, so from here, let's go ahead and actually calculate this average temperature change. And so what it's going to be is it's going to be 1 over 20 times a bunch of stuff. Now I'm just going to go and get areas of rectangles here. So my first base is 4. Since I'm pulling the height from the left side, the height's going to be 55. So it's going to be 4 times 55 plus 5 times 57.1 plus 6 times 61.8 plus 5 times 67.9. Again, where did this 5 come from? This 5 came from the base of the second rectangle. 57.1 came from the left side of that second rectangle. Again, the 6 came from this distance. 61.8, left side of the rectangle. 5, base, 67.9, the height of the left side of that rectangle. Okay, so let's see what that is. Well, I'm going to go ahead and bust out the handy TI Inspire for this. And so what I've got is I'm going to go and add up all of these first, and then I'll just divide everything by 20 at the end. So 4 times 55, whoa, there we go. 4 times 55 plus 5, 57.1 plus 6, boom. I get 1215.8. But remember, I'm doing average values. So I'm going to go and divide that by 20. Boom. 60.79 looks like is my grand total. So 60.79. Now let's go and look back to the original question. What is the original question actually asking? Use the data in the table to approximate that. We did that. Very good. That is the average temperature of the water on 0 to 20. Okay. Does this approximation over or underestimate the average temperature of the water in those 20 minutes? Explain your reasoning. Well, that kind of goes back to why I drew the graph all funky like that. The reason why I did that was because it doesn't matter what your concavity is. All that matters is that your Riemann sum being from the left side is going to be an underestimation. You see all this space right here? All this space that we're not getting every single time. Now, why is that? So we can definitely say the approximation is an underestimate. Most definitely an underestimate. It's the because that we need to check out. Now, actually, they gave us the answer to this question before answering it. They just didn't realize that they gave us the answer, or they did, and they just want to know if we caught it. If you read the problem again, one of the most important aspects about this table is that they tell you this. They tell you that the function is strictly increasing. Okay? So if the function is strictly increasing, why the text turned purple? Okay, keep it that way. We just have to justify using the information that they gave to us. The approximation is an underestimate because W of t is a strictly increasing function. And therefore, a left-hand Riemann sum will have rectangles below the curve. Bam! That's all you have to write for that. Okay? Alright, let's take a look at part D. Part D says, for 20 to 25 in minutes, the function W models the water temperature. It has the first derivative given by this cosine problem. Based on the model, what is the temperature of the water at time equals 25? And this text just turned, there we go. What is the temperature of the water at time equals 25? Okay, so we are given this function here. For part D, it says W of t equals this strange cosine. And if I wanted to find the temperature of the water at time equals 25, another way of looking at this, because we've seen this problem a couple times before, it's almost like finding the position of the particle at a certain time. So if I'm given the rate at which the water temperature is changing, and I wanted to find the temperature of the water, I'd use integration, right? So I'm going to integrate, looks like from 20 to 25, it looks like. And there's a couple of reasons why I'm doing that. Well, one, it's because it gives me W of 25. That's what I want. I want this. And then minus W of 20 being my lower bound. I think they gave me that. I think they did. It's in this table. Yeah, W of 20. Hey, what do you know? W of 20 is 71.0. So I'm going to go ahead and punch that in there. That's 71.0. It's being subtracted from W of 25. All I have to do now is to use my nifty calculator to figure out what that value is. And so I'm going to go ahead and do that. Let's go ahead and punch this thing into our calculator. I'm going to put it in a graph. Or you can just punch it in. It doesn't really matter. 0.4 rad x cos 0.06x. Okay, kind of a strange graph right there. Kind of a strange function. And so now I'm just going to figure out, well, what is the integral from 20 to 25 of f1 of x dx? Well, what that is it's this strange 2.043154699 number. Okay? Now, from here, it's just a bunch of algebra 1. I'm just going to add 71 to that number. So, I'm going to take my answer, I'm going to add 71 to it, and I get 73.03, blah, blah, blah. So I'm going to go and kick that over here. So, I know that W of 25 is equal to 73.043154699. And there we go. That's part D. Pretty straightforward FRQ, I believe. Yeah, we'll have to see you in the next one. Hopefully you got this one.